for inviting me to speak in the physics Coloquium. I'm a frequent visitor of Bar-Ilan University, being part of the INREP initiative that the whole is running, and of course meeting some friends that we know each other very well for quite a long time. And I will tell you about, well, I will start with, I will mostly focus on coherent control of multi-level molecular rotors, but I will also tell you a bit about the other stuff that we're doing at University. So this is my group. Daniel moved to industry, and Dina is now postdocing with Julia, and this is Sumitra who joined the group, but I didn't have his full photo, so I just took Daniel's body and put Sumitra's head on, and it seems to, it's okay because we use the same apparatus. Okay, so I will start with just maybe 10 minutes of the other stuff that we play with in the lab, and then I will go to the main part. So we call ourselves the terahertz group. Terahertz, because we use these nice fields of terahertz frequencies. These are located between the millimeter and the infrared waves, microwaves, and the infrared. 1 terahertz is 10 to the 12 hertz. So if we wave numbers 4 millielectron volts or 300 microns, choose what the unit you prefer to work with. There are several sources. People have been talking about the terahertz gap, the fact that there's no good sources for this kind of frequencies because they are too fast for electronic sources and too slow for optical sources. But actually, this gap is bridging and have been bridged, in my view, although people are still trying to develop more sophisticated generation techniques. I won't go through the ones that are available now, and there are several others that are not represented here. And I will just tell you in a few minutes how we make terahertz fields. But there's another important thing about terahertz which I just really want to stress. People have been talking about terahertz applications for the last 20 years. This is what made many people very upset about terahertz people, because people have been talking about looking through clothes and remote sensing and concealed weapons and knives and whatever. And if you're missing a chocolate bar, then terahertz can find it for you, as you can see here in your Kindle. And explosive materials that has some fingerprints in the terahertz regime, and some illegal drugs and some legal drugs, and some electronic devices, imaging and so on, and biology and the medicine and whatever, and wireless and who knows. And the art conservation, which is actually used, people who use terahertz fields for this motivation. And reading a book without opening it, not sure why we need it. This is something that people have been suggesting, and they're actually publishing this, I think, in Nature Communications. Really, I'm really proud to say that I'm not doing any of these things because most of them don't really work, and what we are interested in is in pure scientific research. So what do we do? And I will talk about these three very briefly. I will talk about just a few words about terahertz spectroscopy of batteries. This is an application, if you'd like. I will talk about laser-induced plasma in air, strong coupling, things that we are working together with a group of Carl Schwarz at the University, and I will then talk to you about the main topic for today. So first, how do we generate terahertz fields? So there's a very nice and efficient way to do it. Actually, not very efficient, but you can generate very strong fields because the demonstration of this technique is such that you can really pump it with whatever you have in the lab. So this is a nonlinear process of difference frequency generation in a lithium niobate crystal. And there's all kinds of problems that have to do with phase matching that are solved by imaging the reflection of a grating, what is known as tilted pulse frontal generation. Never mind the details. What is important is that we get strong terahertz pulses out of this generator that we build in lab, or we set up in lab. And we can get to several hundreds of kilovolts per centimeter field strength. At the peak of this 1 picosecond single cycle pulse, this is a measurement. This is how it looks. You have a field that oscillates once, about once. And the integral over this is 0, like every propagating electromagnetic field. And at the peak here, people have already measured 1 megavolt per centimeter. We have 100, 200, we don't need more than this. But this is just a matter of pumping it harder and tweaking the system. The usable bandwidth of this pulse that I'm going to talk about is about, the Fourier transform of this is about 1.2 terahertz in bandwidth, so between 100 gigahertz or so to 1.2 terahertz. So this is a very broad pulse in the terahertz regime, right? It includes several octaves of the frequency domain. And here's the first thing I want to just tell you about that we recently have been doing with these fields. We have been trying to develop a technique that would allow us to monitor the changes that occur in batteries as they are cycled from charge, discharge, and so on, as a part of the inlet center here at the Bar-Ilan. Terahertz spectroscopy of batteries, just very briefly, what we do is we take a terahertz, this terahertz pulse that I showed you, and we shoot it at a battery that we added a window that would allow the terahertz to pass. On this window, we also deposit the anode. In this case, it's a silicon nanoparticle anode. And the nice thing is that we can see the reflection. This is in time domain, picosecond. So this is the reflection on the first interface of this window, which is the air window interface, which is basically doesn't change because this is outside the cell. And there's this reflection coming from the interface between the anode and the electrolyte that we diagnosed in a different. We make sure that this is the case. What you see here is two transients, different events. One of them before we started the electrochemical process, and the other one somewhere in between after charging or discharging. Okay, you can see that there's a quite difference in this back reflection. When we analyze it, we do it by. It's not a spectral analysis, it's just basically a measure of the energy, if you like, or the reflectivity of this back reflection. So we just analyze it by the ratio between the integral over this to that. So this just acts as a reference. This doesn't change throughout the experiment. And we plot it against the electrochemical process or the current and the voltage. You can see that there's a very nice correlation. There's something that develops. This is the reflectivity. It goes by a factor of almost 4 as we discharge or we lithiate the anode, and then it remains constant, as you can see, or fairly constant. And then only when we delithiate, nothing happens. But when we finish delithiation and there's something happening, then this changes. And then we make a very, and these are some more advanced results of different timing of charging, and check whether our assumption or our observation is correct. And what we can just say as just a take-home message is that this measurement is specifically sensitive to the SEI solid electrolyte interface layer that is generated at the during the first charging of the cell. This is those of you that don't work on batteries probably don't appreciate it, but this is a very, very elusive entity that is crucial for the life of the battery, for the lifespan of the battery. This is something people work on very, very strongly, and we didn't know that this is what we'll see, but from all of the correlation between the electrochemical and the terahertz measurement, we can deduce that what we are specifically sensitive to is this specific layer. This is, by the way, the same layer that when you bought a device that operates on batteries a few years ago, they will tell you charge it for 12 hours and don't operate it. This is because it is generated, it is formed on the first charging of the battery, and it's crucial that it is formed fully and to provide a stable layer like this. Okay, so this is, well, we published this, but this is just a work in the very first steps in this, because we have to do a lot of other stuff here, and we are building the system that will now provide 3 terahertz bandwidth, so we can really take spectral, look at the spectral resolution also, and try to find the specific frequencies that are changing throughout that report maybe on the materials or whatever happening.
What is the underlying physics? So why using terahertz and not microwave and infrared?
So infrared, so basically if you just look at the anode, you'll see that this is usually a very absorbing black substance that infrared usually just don't penetrate through. People are doing also infrared in situ or around the terahertz, infrared spectroscopy and other stuff as well, of course. But in the terahertz, it is not like, I have to say, we didn't know that this will be the end, the outcome. This is just after 4 years of working on this with the electrochemical groups, this is the conclusion. Why is it working? Well, basically what changes on the interface of the anode and the electrolyte is a strong change in the dielectric function, which gives rise to what we believe is just Fresnel reflection. But this is so strong in the terahertz regime that it reports, to the factor of 4, just a jumping factor of 4 in the reflectivity, which by the correlation we can deduce that it has to do with the SCI. But we didn't really, I have to admit, we didn't really play it. Someone actually asked me a few weeks ago, why did we go into this business at all? I said I was young and I needed the money. But actually, now that there's no money from INREP anymore, this is interesting because, well, the result.
This has nothing to do with the length scale of the wavelengths and the length scale of the layer? Or something?
The layer is few nanometers. It's few nanometers. I mean, we did some work with Gil Markovich and his team. They are trying to develop conductive windows, like for ITO, but from other materials. They did some grow some nanowires of gold and so on, and we try to characterize it, just see what happens. And of course, also even though they just generate these thin layers of like 30 nanometers or so, the reflectivity changed very, very strongly in the terahertz regime. Why this is happening?
What about the dielectric relaxation? Because this should give you a time scale. People can you can do it. You polarize this system, maybe you can, then you see how fast it relaxes, corresponding to this.
For this, I guess I would need to do some farm products. Yeah, but this is like this is happening within the 1 picosecond pulsation. This is just we just shoot a terahertz pulse and we detect it with some detector far away. It's not like we do something to the layer and then watch how it relaxes. Although this is something that we can try. Okay. And now the thing is that we are interested in monitoring the plasma formation from its very early stages of growth. Before you have something, and just one step after you have something, and so of course to follow it, how it changes in time, the time it takes to decay or to recombine and so on. Okay. Very briefly, and maybe I think I'm more than
20 minutes.
Oh no. Let's start over. Okay, let me skip this and just say that we are working on strong coupling. Those of you who know the field probably appreciate it. Those of you who are not probably think that this is just a fake. But I just tell you that the only thing that we did until now, together with Tal Schwartz, is showing that we can have strongly coupled material inside fabric cavities and observe what is known as the indication for strong coupling, which is this generation of these two polaritons. These are called polaritons, upper polariton, low polariton. This is just hybridization of a cavity that the resonance of the cavity is, dictated by the width of the distance between the two mirrors and the absorption line of the material that you put inside are at the same frequency. When you do this, you get this funny splitting. Now, that's one thing that I want to say about this is that, this is something that you can explain classically, almost just classic electrodynamics. You don't need any quantum, nothing. You don't need to think about quantization of the field. You don't need anything. You can simulate it classically. What you cannot do is explain how this affects chemistry. And it seems that this is a crazy entity. These strongly coupled materials have been now shown in many papers to actually change the nature of the material itself. The chemistry changes. If you see a reaction that the branching ratio is 20 and 80, by strongly coupling it, you can take it to 90 and 10, or anything in the middle by tweaking the strong coupling. And that doesn't need any light, by the way. This is done without light. The light is just a probe for the distance or for the strong coupling, but now you turn off the light, you do the reaction inside this cavity, and you get the different chemical reactions. People don't understand this. We certainly don't understand this, but we are now trying to set up a group of people that would be strong theoreticians and some experimentalists, actually, Thomas Everson, who actually invented this field as well, to try and really tackle the very, very basic fundamental physical problems of this pure magic until now. This is the collective effect of the molecule inside the cavity. It's a crazy thing, and nobody, believe me, nobody understands this, but the results are astounding. Okay, so now I go to the main part of my talk and try to skip several things because I wasted too much time on this. Okay, so this is how it looks in the supplementary information section. This is actually how it looks in the lab. And there are several systems here, but the basic idea is that we have the terahertz generation module, the routing, and the interaction setup for F setup or something else, and the detection of the terahertz field. Okay, and the topic of the field that I'm trying to actually focus here unsuccessfully is the coherent control for molecular rotation. This is a long-standing goal of physics and chemistry, having to do with the fact that because molecules interact with light according to the angle or the projection of the field on the transition dipole of the molecules, it means that when you measure a bunch of molecules without any order, you basically average over the entire ensemble, the distribution of the ensemble. So people are trying to make this into this. And the reason is to expedite and allow and enable all kinds of molecular frame spectroscopy. But for us, and actually for the most of the people that are working in this regime, or this field in the last years, actually it's just a very elegant platform for studying molecular dynamics and light-matter interaction in general. Because most of the results actually led not to molecular frame spectroscopy. This is nice for writing a proposal for ISF, but the things that came out from here are much, much better in my view. Okay, very basically, why terahertz? So an ultra fast or just a non-resonant optical or the ultra fast people, you know, it's usually 800 nanometer pulse. This pulse drives molecules to align. Namely, it induces a torque that because of the acts on the molecules through the anisotropic polarizability of the molecules and not through the dipole, making them, they can make them aligned along the z-axis, but half of them would look with the dipole up and half of them with the dipole down. It is not interacting with the dipole, so it's not dipole selective. Terahertz fields oscillate at about 500 times slower rate. So the dipoles can follow the terahertz field. And what you get after the terahertz field is actually this. You get orientation. So this is the difference between alignment and orientation. Okay. And the basic rules of optical field doesn't matter because it is dictated just by the level spacings of the quantum mechanical rotors, these molecules. So when you shoot a pulse at t equals 0, this is an optical pulse with the same method as the terahertz pulse. It aligns the molecules in this case, and classically you would expect nothing to be observed afterwards, but of course, because molecules are quantum mechanical entities, they continue and rotate, and every, in this case, a revival period, which you can explain just by looking at the phases accumulated by the different eigenstates of the rotor. Every now and then, every period, which is depends on molecule selecting, appears another event of alignment and anti-alignment and so on. And this is how basic signal looks like. And this is for alignment, this is for orientation. Here there's an optical field or VIR pulse. This is a terahertz pulse. You can see that basically it's the same. And when you want to, well, this appears twice, but not with reverse phases. We won't go into these details because this is not important. What we wanted to do at some point is to measure the decay rate. Just the decay rate is a function of pressure or density or whatever. And when you want to just analyze this, you would like to take maybe the peak or the peak-to-peak value of each and every line and just write some exponential decay. But you cannot really do this because these...
Why the strength of the pulse decays?
It decays because of, well, several things, but mostly collisions. Mostly collisions between the molecules. But not only.
Saying that the molecules are, for some quantum mechanical reason, they're getting out of the aligned position and they're starting to oscillate, and then you align them again.
No, I'm not aligning them. I'm giving them torque. Just I'm torquing these molecules, but the torque, the strength of the torque depends on the initial angle at which the molecule was situated with respect to the polarization of the pulse that torqued all of these ensemble. And from the quantum mechanical evolution of this thing, it revives every revival period. For this molecule, by the way, it's about, for OCS molecules, about 82 picoseconds. Every 80 picoseconds, there's an event of reorientation because of these funny phases that accumulated commensurate phases. But I hit it only once here.
It's empty to the four.
This is
what's the y?
The y is in this case, it's birefringes, which tells me about the degree of alignment of the molecules. In this case, it's the amplitude of the field that is emitted from oriented molecules, because the measure of oriented molecules is is a macroscopic dipole formed once they are oriented, which emits free induction signals, which we measure. But if you look at both of them, it's something that you need to characterize in a different way. You cannot build on the peak-to-peak value of these peaks of these signals, because they change as a function of time. They change because of a well-known phenomenon of centrifugal distortion. As the molecules rotate faster, they slightly elongate, right? So the harmonic frequency spacing between the quantum mechanical rotor, something that we know from from quantum mechanics 1, right? This is one of the only models that can be analytically solved. This slightly changes, and you can add this correction term, which is given by this T, J squared, J plus 1 squared. These are the quantum potentials. If you look at it just a bit more mathematically, this is just a dephasing mechanism. Dephasing mechanism that looks like a third order chirp in the J, something that corresponds to J cubed, J squared, and J. This leads to the change of this shape at the first revival period, to this, and so on. So we said maybe we can just rephase it. If this is a dephasing mechanism, we can rephase it like people do in NMR. People do this in NMR since the 50s. They take these many spins and they do what is known as an echo experiment. Hans echo experiment, or spin echo, 1951. It's a well-used technique. It's something that is very, very broadly used in many, many disciplines, including even MRI, of course, or heavily used. How does it work? You apply a pi/2 pulse that mixes these two levels of the spin, then it evolves on the Bloch sphere, then you wait for some time, you apply pi pulse, which actually rotates by 100-degree rotation on the Bloch sphere, and then things that accumulated phase apart until during this time accumulate the same phase but in opposite direction at this time, like what is shown here. Is the runners on this. Okay, so we need pi/2 pulse and the pi pulse. In fact, people have been doing this in electronic transitions, in vibrations. This is commonly done in 2D IR spectroscopy. Usually, what you do is echo experiments. But the interest in these echo experiments in rotations started only in 6 or 7 years ago. And the reason is that people think that since this is a reviving, you apply the pulse now and then you can measure it for hundreds of picoseconds with these quantum rotational revivers. You basically people have been calling this echo, rotational echoes. But it's not an echo. An echo is something that happens when you reverse the phase and you actually effectively make these phases accumulate in negative direction. In this case that I showed you before, when you apply one pulse and the wave packet revives, it's because the phases accumulated an integer number of 2 pi's between all states, but time always propagated forward, or the evolution always went in the same direction. So I wanted to do the opposite, to reverse the direction after doing 2 pulse experiment, like Han said, and this is what you can see here. So this is simulation. First pulse applied here, then we have to wait for some delta time, some time, then apply another pulse, and the same delay after the second pulse, we get this echo signal. And this is a measurement of this echo signal. You can see here the responses to the first pulse only, to the second pulse only, but here you can see these echo revivals, and of course they accumulate phase because of the same centrifugal distortion. I mean, this is not something that we can stop, right? This is an entity, or this is a feature of the level spacing that is dictated by the molecule, not by the field. And if you do the same experiment, but you just change the delay to 140 picoseconds in this case, so the first pulse is actually somewhere here, second pulse is here, and then we just measure, you can see that we can look at the wave packet or this echo signal on the way to rephasing, then fully rephasing at what we write here 0, and then continue to dephase according to the centrifugal distortion. It's nice to see that in the, if you just reverse this, you get this one. If you just reverse this one, you get this one. So I think you understand it. The problem about this echo spectroscopy technique is as follows. We need a 90 degrees or pi over 2 pulse. But what is a pi over 2 pulse in a multi-level system? You cannot even define it because the pi pulse is, right? The pi area pulse is given by a single transition that you know the dipole, you know the bracket with the dipole inside it, the transition dipole moment, you know everything on this specific transition, you can calculate pi or pi over 2 or whatever. But here we have a multi-level system. All of the states, we have tens of states populated at time 0 at under room temperature. We can maybe, we can do a transition between 9 and 11, and actually we do. The transitions go from each and every level to 2 levels above due to the selection rules of this Raman type excitation, but we cannot stop this from going to 13 or higher. So we don't have a 2-level system. A 2-level system is something that when you move everything from the ground to the excited, and you continue to pump the system, it goes from the excited to the ground. In our case, it goes to the excited. During this time, it goes from the excited to the another excited, another one. It's a multi-level system. So we cannot really calculate even what is a pi or a pi over 2 pi. But when you simulate and you see the dependence on the pulse intensity, you see that this is a linear with the first pulse, meaning one interaction, one Raman type interaction in this case, and it starts as the power of 2, right? Square dependence on the second pulse, but then it reaches this peak. It actually looks like a sinusoidal square. This is also, this is the experiment, which of course fits the simulation here. And in fact, this is already mentioned in the paper by Henning. So I just put it because I like the title. It's fundamental and not so fundamental properties of spin echoes. So, okay. So we understand, I think, how it works. We know how to simulate it. Everything is nice. The real problem is as follows. When you want to measure, what do you do with the echo experiment? In an echo experiment, what you would do is to measure or decipher between decoherence and dephasing, right? You want to know that if something is rephasable, it only dephased. But if it is not rephasable, for example, collisions, emission, whatever, decay, real decay, something that took the energy or totally mixed the phases that you had because of some interaction, it is not rephasable. This is how you, this is exactly what you do in an echo experiment. For this, you need to do the following thing. You have to take this 90 degrees or what, and to take an echo measurement, and then change the delay between the first and the second pulse. So this is the waiting time, they call it, or the mixing time, or whatever. There are all kinds of names in the literature about this. But this is what you want to do. And if you record the echo signal as a function of the delay between the first and second pulse, and this decay tells you about decoherence, not dephasing, because this kind of signal rephased everything that could be rephased, could be fixed. Okay, So if you have a decoherence, you have this kind of decay. If you don't have decoherence, you have this. You have a flat line. Nothing happens. Everything that dephased can be rephased. But this is not what we have. Here is the dependence on the delay of our measurement. This is a simulation without decoherence, without anything, only dephasing. So the full dephasing, or just dephasing because of we have multi-levels and multi-frequency. You see that the signal changes very strongly as a function of delay between the first and the second pulse. So if we make a measurement as a function of delay, this is what we'll see. We certainly won't have a flat line, and we certainly would not be able to extract an exponential decay or whatever decay from this, because this is just not flat, this is not constant. Okay, the question is why? So this is a measurement, this is the simulation. This, by the way, happens 4 times within the one revival period of the system, but this is more important. And I think that this is maybe the most relevant slide in this talk to the title that I sent you. But of course, I have several other stuff that are newer, but maybe this is the main take-home message. The thing is as follows. This is, we want to understand why the peak of this echo signal, when we fixed the intensity of the first pulse and the second pulse, we don't change the intensity, just change the delay. Why it changes like this? Why the peak, the maximal efficient echo appears at 1/8 of the quantum revival? And the reason is because of interference of multiple quantum pathways. So if you think about the pathway, you would write a Feynman Feynman diagram in optics. It's an optical Feynman diagram that goes from population step through some coherence to a different coherence, whatever. But here, this is not enough. Here we have to consider several of these and see how they interfere. And for this, we just use the density matrix formalism, or the density matrix. This is inspired, presentation inspired by the density matrix formalism. So you have here the population terms that you start with. You apply the first pass. First pass, we know that it interacts once because we saw it's linear. The signal is linear with the first pass, so one interaction. So one Raman interaction, for example, takes me from here to here. Really? Okay, I think I'll come back for the next part of it next week. But okay, we'll finish in 5 minutes. This was ready, by the way, about a month ago. The things that I worked in the last week was the rest of the talk that I worked. Okay, so but this is the take-home message. It's okay. So this is what happens on one Raman interaction. Okay. To rephase this coherence term, we need to go from here to here. This can be done, and this happens after some time that we waited between the first part and the second part. This can be done with the second pulse that interacts twice. This is why the quadratic dependence. 2 Raman interactions. It can go, for example, from here to here and from here to here. This takes at the same 100 femtosecond pulse. Okay. The phase that accumulated in this coherence term is given here. It's the waiting time times the frequency, the transition frequency between these two states, J and J minus 2. Now, there's another pathway. The same pulse, same first pulse could have taken me here. And now I've waited for the same delta t, but now the phase that accumulates is this phase, because now it's J and J plus 2. And the second pulse, the same second pulse that did this, will now take me from here to here. And these two pathways, they started from the same position, they went to different coherence terms in the density matrix, and then they meet again at the coherence, at the rephasing coherence term, and then they interfere. But this is why the time between these two pulses dramatically affects the result of the rephasing, the signal that you saw going up and down, this signal. Okay, and we see here that the phase accumulated between these two is given by e to the minus, the 8 pi delta t. This is in units of the revival of the quantum revival period. This is why delta t equal 1 over 8 makes this a pi. Why do I want a pi phase between these two systems, between these two pathways? Well, the reason is that let's say that we didn't have a pi. Let's say that I don't introduce a phase between these two pathways. To do this, I can just think about two pulses separated by one quantum revival time, or just let's think about one pulse and consider the three transitions that it can apply at t equals 0. So I have this, but the delay is 0, delta t is 0, so the phase between them, accumulated between them on each one its coherence is 0. Now this certainly doesn't give a rephasing, right? This doesn't give an echo response. So it just tells me that the inherent echo signal is distracted by the fact that the phase accumulated between these two pathways is such that it gives a destructive signal. There's no echo signal. Or how do I make a destructive signal a constructive signal? If I have 0 phase between them, which is destructive, I just introduce a pi to make it constructive, right? And this is what we did. 1 over 8 of the revival, the pi phase between them is accumulated, and you get a fully constructive signal. And this is why the pi. And of course, at the different times during it, it will be 3 pi, which is just like a pi, or 5 pi, which is like a just like a pi. Okay. I think we have to finish, but I just tell you that one thing that I mean, well, the thing is that in order to actually do the echo experiment now, you need to find the resolution for this problem, because at different delays, I'm going to have a different signal. We found that for each delay, we have a different signal intensity, right? This is the problem. But we found that if we change the intensity of the second pulse, the maximal intensity that the second pulse, the maximal echo signal that will be generated by the second pulse when we go to the, when we change the intensity, the optimal echo is conserved. This is what you see here. At different times, the peak is always at the same line. So now you can make an echo experiment. How do you do this? You change the delay, but you don't change only the delay. When you change the delay, you scan the intensity of the second pulse, just record the maximum. I don't care how much it is in milliwatt or whatever, just find the maximum. The maximum will be lowered by the fact that it decays, but the maximum will tell you what is the signal, will give you the same theoretically rephased signal. And we showed it here and published this. And this is really, now I have just another 50 slides that I want to talk about, but this is the, okay, this is the first part. Okay.
Next. Time for some questions.
Like the question could be, what do you have in the next slide? Very good one.
Actually, I have a silly question about the rephasing diagram that you showed us before, about the second pathway.
Yes.
And why is it going back to the left and not to the bottom, to J and J plus 2? I know it might be silly, but
it could.
Of
course, yeah. I mean, everything is open. You can go wherever. But if you want, if you ask yourself, what would give me the echo, the rephasing echo signal, is taking the coherence that you made, and bring it to the Kettbra entry, right? Of course, this is true. Of course, the second pulse does. Second pulse can not, also takes me here. It takes me here. This is true. And these are other signals that we didn't talk about. they can be measured by other means. But for the echo response, this is the entity that you're looking for, making this into this.
Yes, so the battery cat, but for the second pathway, it doesn't go to its cat because it's supposed to be on the bottom. It's supposed to be J&J plus to right. And this one's supposed to go down to its cat.
It also goes down to its grid.
Oh, okay.
Of course. I just showed you
a specific one.
Of course,
okay.
Because otherwise I would have needed to put all the lines here. And I showed you the one that contributes to our signal that's of interest. But there are, of course, many, many others. By the way, the fact that there are many, many others is the reason for which the rephasability that we can achieve is never 100%. It's about 50%. We don't understand yet exactly why this number is conserved. We have found that it does not depend on temperature. The initial population, you can go from 3 Kelvin to 3000 Kelvin. It's the same. You can go it doesn't depend on the rotational coefficient. It actually depends on nothing but the architecture of the level spacing of the quantum mechanical world. And actually, this is what is written in the manuscript that Dina has written before she went for postdoc, and I've never had the time to go over yet, but soon.
So this is based on the rotational energy levels, right?
Yes.
You had previously also the second term with the D times J squared.
Yes.
Yes. So here you actually forgetting about that part. So you're assuming it is small.
Yeah.
But the question is, if actually you wanted to investigate that non-linearity, I call it, which is not less trivial or not the usual type of rotation, you could also have resonances with that one, but then they would depend also on this factor D that you call.
No, of course, you mean the accumulated phase has to be taken, the difference between the D times J plus 2 squared
so
J
I don't
plus
see
50.
D here. I mean,
Right.
So,
This is just for the explanation, but I mean, when we calculate, of course, we calculate with the D, of course.
okay.
But this is just because you want to follow the reason for which it is pi. Now, the ratio between D and B is about 10 million.
Okay, that's
right. So if you think about this, the short times,
I didn't know that
it's not really important. It's important at long time. It will become more important. It will tweak by.
I didn't know that the ratio is.
Yeah, it's about for the molecules that have large centrifugal distortion is 10 to the minus 5, the ratio between D to B. The ones that are small is 10 to the minus 7. So it's on average, it's about it's somewhere there. We actually chose a molecule with significant D compared to others, which is the CH3I. Where you can see this observed at very short time of a few quantum levels. But the interest in this is certainly not because of the rephasing. The rephasing was the interest in rephasing is not because of centrifugal distortion. Centrifugal distortion, if this was the only thing that dephased the molecule, I know how to calculate it from after one pulse from the time domain. I don't make this. It's because of the environment, because you want to use this to study something about the interaction with the environment, other molecules, binary mixtures, stuff like this, or very, very high pressures. People have been using this recently in 43 atmospheres, and where there's no quantum environment. Everything dies after, let's say, I don't know, 20 picoseconds. You will never reach the signal at 80 picoseconds. So you can never measure the decay rate. You just know that you don't have a signal. But in this case, you can, because you can change the delay as much as fine as you want.
Okay, thanks. Shall we again?